Can you hear me? This doesn't. Hello?
That's
There.
muted.
Hello? There. Okay. Got it. Okay. Good morning. My name is Lauren Garten. I am an assistant professor of material science and engineering at the Georgia Institute of Technology. And it has been really great to see all of the work in the last week, particularly on 2D and complex ferroelectrics, things that back in my local research community are considered to be very exotic and kind of strange. So I'm really excited to find a community where I can come and share some of this work in the future. But today I'm going to talk about something a little different. Here, I'm going to be discussing work that was done in collaboration with Margot and Peter Finkel at the USA Research Lab on using ferroelectric phase transitions to enhance converse magnetoelectric coupling in artificial multiferroic heterostructures. So Dr. Linda Mann did a great job of introducing magnetoelectric coupling. So I won't belabour this too much. I will say here that what we're looking at is the converse effect. So we are looking at either inducing or manipulating magnetization due to the presence of an applied field. So just like piezoelectricity, there's a direct effect. Now there are a lot of applications for which this is interesting, right? You can have magnetoelectric sensors. You can also have energy harvesters, and there's a number of types of recently proposed ultra low energy expenditure magnetoelectric spin orbit coupling logic, right? Where if we have the right materials, we would be able to make extremely efficient types of logic. But the difficulty here is that while magnetoelectric coupling can occur in a single material, it's very rare. It often occurs below low temperature, and the coupling is particularly weak. So I have a couple of examples here. So for the terbium manganate, actually I'm not sure if that's the right localism for that, but the single phase structure right there, right? Your coupling coefficient is about 10 by minus 11 at 3K. And there's a lot of great work that's still going on trying to push up transition temperature to increase coupling, right? But as a community, we've taken the solution of making composites. So separating the electrical responses handled by one material and the kinetic responses handled by another. So even though this was discovered about a decade ago now, iron rhodium is still one of the materials to beat. Right, so it goes through a temperature-induced metamagnetic phase transition above room temperature, right? And it's about a 1/5. So that's what we're trying to beat. And ultimately, we want to have something that's not necessarily temperature modulated, right? So when we're making these artificial multiferroics, right, we're taking a ferroelectric and a ferromagnetic material and we're coupling them. So we're not going straight from our polarization, our magnetic field of polarization or our electric field of magnetization. We're actually going through an intermediate step, which in this case is piezoelectricity, right? So we have an electric field and that causes a strain in our piezoelectric material, which would then come up through an interface to our magnetic material, which through magnetostriction leads to a change in our magnetic orientation, right? And so there are other ways that you can have magnetoelectric coupling. I'm not going to touch on those at all because strain is one of the most effective that we've found so far. And the coupling coefficients are typically worse magnitude larger than what we find in a lot of the single crystal materials. But this is still not enough to reach the full potential of a lot of the applications that I was talking about, right? So what do we need to do? And in a simple sense, you could just think, okay, let's start by increasing the response for each of the constituent properties, right? So in this case, what are we going to do to find the largest amount of strain for a given amount of electric field? And from the last few days, you probably appreciate that one of the best materials to do this with is a relaxer ferroelectric, right? So these have historically shown that they have large strain reduced electric field, in part due to piezoelectricity and electrostriction. And in this case, we're particularly interested in a lead indium niobate, lead magnesium niobate, MPT, in part because it has a large piezoelectric coefficient. It has a broader temperature range than some of the other common relaxer-based materials. I'll be honest, in part because it's commercially available, and also because it exhibits a ferroelectric to ferroelectric phase transition, which can be modulated with strain or electric field, right? Because ultimately, we're kind of agnostic as to the mechanism which induces the strain, right? It could be piezoelectricity, it could be electrostriction, or it could be a phase change, right? And if you do domain engineering, where you cut along specific directions and you pull along specific directions, what happens when you go through your rhombohedral to orthorhombic phase transition in these ferroelectric crystals is that you can induce a large amount of strain. And that's what's shown here, right? So for small molar stress, you can have a relatively large change in strain, and the position of this will change under different electric fields. So it can be electric field driven, it can be stress driven. And you can imagine that by poisoning a system right out there, right, you could have large changes occur in the systems for small amounts of stress, right? So that's the key here. So this is something that was tried initially, and in these heterostructures, which I'll describe how they're made here in a second. But I just wanted to say that if you look solely at just applying stress to these composites in order to reach this transition, it actually leads to relatively low converse magnetoelectric coupling, which is surprising. This is kind of counter to what our initial hypothesis was. But ultimately, we realized that there is some kind of isn't the best word for this, but there's some kind of limited movement that's occurring in our magnetization, right? It's getting to the point where it's cold hot and can no longer respond. The other important thing to recognize, and this is a optical profilometry of a witness wafer that was put in at the same time of a sample, and from the curvature, we noticed from this, and you can use Stoney's formula and pull up the exact stress in your film, but just from sputtering at room temperature, relatively gentle conditions, we can induce a large amount of strain into our samples. So we were at a strain state which was greater than what we thought, and it didn't have very much coupling. So the question is, what can we do? We still want to be able to use this ferroelectric phase transition to its full extent, right? Oh, and these are the same type of crystals that Peter was talking about yesterday, with a large difference in both cases, electricity and optical response as well. I should add that in there. So we want to use this ferroelectric phase transition, right? So what can we do, right? And the idea here was, okay, and Margaret was really changing this. She said, okay, what if we grew and under strain, right? What if we stressed our samples and grew them that way so that the magnetic film would be more relaxed as we start to approach this ferroelectric phase transition, right? And so that is what we did. And we went through the process of comparing films that were both grown under stress, so they had this inbuilt strain, and also films that didn't be measured while stressed, so they had some time. So the materials that we're working with, we sputtered a magnetic film of iron cobalt with interlayers of non-magnetic silver. We did this as a stack, composite stack, and we did it on top of our single crystal PIN community. And for every sample set, we always did it 2 in tandem, right? One that was not stressed and one that was stressed, right? So that we knew that they were done in the same conditions, right? And so it looks something like this. Some graphic directions here. Our bottom electrode was our gold, and the top electrode that we used was actually our magnetic material. And this is the very simplified design of experiments here, where we're looking first at the unstrained conditions, and then looking at the impact of either inbuilt or applied strain on the converse magnetoelectric coupling. So we had a fixture shown here on the right that we used to apply stress while we were growing. We used a similar thing to apply stress while we were measuring using vibrating sample magnetometry, right? And in this case, what we want to see is we want to rotate our sample in this plane so we can look for the rotation of that easy axis, right? And so on the right, these are LMH loops with pins to our PE loops, which we've seen a lot this week here, right? The one thing to notice is that when we apply, say, a positive 2 volts per centimeter, what we see is that our easy axis is changing as we rotate our sample from from a small amount at 0 degrees, and then indicating that our easy axis is where it is easier to align your magnetization, is closer to 90. And if we go through, we plot overhead magnetization and normalize to our separated magnetization, we get a polar plot on something like this. where the black is with zero electric field applied, right? And you can see that with positive and negative field, you have a rotation of your response. This is indicative of a change in the directional momentum of the axis of the line. As somebody coming from ferroelectrics, it was very disturbing to realize that while there is magnetocrystalline anisotropy, which does influence the movement of your magnetization, the truth is it can move as it wants in response to a lot of the strains. So that's what we're looking at here. And this is just highlighting a little bit on the difference in the image, which is zero. So you can see there's a large change that's happening here in your magnetization. Okay, so next we went through and calculated our converse magnetoelectric effect, right? In this case, what we're doing is looking at the difference between our MH loops under electric field compared to those that are without electric field, right? And so this is the data here for the unstrained case, where you can see that as we're approaching the coercive field, magnetic coercive field of our material, right? We see that there's a spike in our response close to 75 and 90 degrees. They are a little bit asymmetric, and I can talk to you offline about that later why. But overall, we got a pretty large response, right? So this is 8 by 96 for 100 volts, which is equivalent to 2 kilovolts per centimeter. So a lot more voltage, or a lot more electric field than might be necessary. A lot more voltage than might be necessary than for a thin film, but still a pretty high response. So the question of the study was, okay, so now we have this protocol. What is the impact that happens when we grow these films under that have inbuilt stress, and if we measure them with inbuilt strength, right? So this is what I just showed up here on the right. The next is, okay, we grew this under a certain amount of strain, and when we look at the polarimetry for this, we see that we do not get rotation during these tests, right? And this is what we would expect. This is consistent with what I've been seeing before, right? Now, let's think about this in terms of measuring under strain, something that has been on strain, right? In this case, we have all of our magnetizations pinned on this position, right? So again, we're not getting a lot of rotation that's happening when we go through these samples. But the thing I'm really hoping for and getting really excited about was, okay, we strained it during growth, or we stressed it during growth to involve the strain. We're going to apply a similar stress to get to a similar level of strain, and the film should relax and be easier to move. And the truth is that didn't happen. So at this point, I about gave up on this project completely. But if COVID has taught me anything, it's that sometimes being forced to sit down and look at data actually brings a lot of benefits, and you find things there that you might not normally have appreciated or realized. So I went through the arduous process of calculating the converse magnetoelectric effect for all of these theories. And actually, it ended up being a really good thing, right? Because for these strain samples, we actually got about 9.9 by 10 to the minus 6, which is on the order of what the current state of the art is. Somebody now, Hama Malay now has something that's slightly over 1, just I think 1.1, 10 to the minus 5, which is a current world record. So I was actually pleasantly surprised, and this worked out very well at the time. This is highest non-resident room temperature, right? And you can see the peaks that are happening here. And yeah, so this is a synopsis of all the different conditions. You can see that we have the lowest for the negative ACME for the unstrained strain case, because it's what we saw before, and the highest for the strain case on 9.9 to the minus. So that's really cool. The question is why? Right? You know, why is the converse magnetoelectric coupling so large when these films that really showed effectively no rotation of the easy axis? And here's this. If you go and you look back on what the MH loops actually look like, for the unstrained case, it's very clear that you're getting this rotation. That the axis along which it's easiest to align your flow or your magnetization is changing as you're applying different alignment fields. But it's not the case for a strained film. Here, what happens is we actually have a change in our coercive field. So if you're taking the difference between these loops, you actually have a large amount of change that can happen very, very, very coarse is, right? And this change clearly indicates that there is a different mechanism which is at play in these types of films than there would be in what we would expect with a traditional rotation. In this case, it's tentatively due to a change in your magnetic domain structure. right? So this could be an interesting way in the future to be able to increase converse magnetoelectric coupling by designing with types of strain that lead to different types of microstructures and different types of domain structures. Now I'm going to conclude my talk. I'm going to say that we designed these artificial multiferroic heterostructures. We have these kind of multiple strain engineering approaches that we can take, right, using ferroelectric phase transitions. We have determined that strain during growth and measurements actually did lead to an increase in our converse magnetoelectric effect, which is not what we first expected. And that there is a change in the dominant mechanism which is controlling CME in these strain films. So with that, I will say thank you, and I will take any questions that you have.
Thank you. Thank you very much. We have some questions. Okay, so yeah, great result, exciting result. So I'm going to go back to the first beginning, the first thing in front of the first slide. You use magnetoelectric for the, as the physics of the coupling between strain and magnetization. Did you look at any piezo-magnetic materials?
Yeah. So we did look at the. Yes. So we did look. We didn't do an extensive survey of different materials, but we actually did look at the piezo-magnetic response of the iron cobalt layers that we were using, which is somewhere in here. Give me a second. Here we go. Yeah. So, and they, right. So another thing that I didn't mention is that we use this layer breaking to decrease our coercivity and to increase our piezomagnetism. So we have the image loops and the piezomagnetic measurements for the iron cobalt interlayer with silver. They're okay. We could do more with a higher piezomagnetic responsibility.
I know, I'm just curious because it might, I know they're not very many piezomagnetic materials, but it might be a way to get a larger response.
Yeah, that's a good idea. I agree.
So, so when you are saying, when you say that you are working, you mean you are an LDC, you are applying a DC bias.
Yes, we're applying DC electric bias. Yeah.
But that's very good. Remember, not so updated details that we're talking about very specific situation. But you have to quantify the maximum at the coercive magnetic field. So I was curious, so ultimately for applications we will be in the see the magnetic field.
Yeah, so there is the potential to have sometimes people put a fixed permanent magnet next to some of their devices so they can offset it. Ideally, we do want to decrease our coercive field as much as possible, which is part of why we're doing the layer breaking. Not quite there yet, but there are ways to compensate for that. But you're right, you want to be careful.
More questions? Yeah, thanks. Oh, exactly.
Yeah, just to go to some regulations maximum value for strain film with the content, but with the goal, I think it is strain that is almost right. So first is significant and is it a problem?
That's a fair question. So I do believe that it's statistically significant because we saw similar trends across a number of different samples. So that's the first. The second part is I was impressed that we already had a very high magnetoelectric coupling in the case of things that were even unstrained, right? You saw how many degrees of rotation and a decent CME. So I would say that, and that's benefiting from this large phase transition, right? So you don't necessarily need to inbuild all of these different strain mechanisms to get to the largest response possible. If you're using this on a device, you might do something that just was only looking at, say,